Hi you guys, this is notes number 8. We're pretty much wrapping up the unit here, okay? Here we are going to pretty much connect the two big ideas that we've been learning. But just to give you kind of a checklist, here we go. Kind of a checklist before you leave for this lesson, okay? We're going to look at something called Hopital's rule. We're going to revisit limits. Okay. We're also going to look at higher order derivatives. And then we'll look at some situations where we have parallel and normal lines. Okay, we'll talk about each of those there, okay? So make sure that you have that checklist. Okay, so first thing we're going to do is we're going to look at Hopital's rule, okay? Now, in a lot of books, okay, originally it was Hopital's rule spelled like this with that additional S. People like to say Hospital's rule, but it's really not. It's Hopital's rule. And it was only recent, maybe about within the last 15 years, that they looked at some original manuscripts and they found the original spelling of this person's name. And it's actually Hopital's rule. So please don't say Hospital's rule, okay? Hopital's rule. First, what is it, right? And how do we apply it? Okay, so let me show you guys through exploration, through logic, how Hopital's rule works, okay? So let's say I had a situation. I'm going to ask you guys, suppose I ask you to find the limit of 2x squared plus 7x plus 3 all over x plus 3 as x approaches negative 3. Kind of like your Unit 1 assessment, right? You had to evaluate a limit. Okay? Now, what you guys would do here is you would first try to directly substitute or plug in chug. You find out that you get something that's undefined. And then, in some ways, you manipulate. You have 2x plus 1 here, x plus 3 all over x plus 3. And then we also take the limit as x approaches negative 3. We find out that we can reduce a factor. And then we have the limit of 2x plus 1 as x approaches negative 3. And then we end up getting negative 5, okay? So here's an alternative approach. So first I'm going to show you another way of evaluating limits, but then also what's the point, right? What is the purpose behind learning an alternative point? So I'll answer both of those questions very soon. So here we go. So here on the upper left, you notice that I have the numerator as f of x. Okay, f of x is the 2x squared plus 7x plus 3. And g of x is the x plus 3 in the denominator. Okay? So don't worry about everything else down here. So here is f of x, to the numerator. And we notice that we want to get arbitrarily close to negative 3, right? And if you notice, at negative 3, we get 0. We get arbitrarily close from the left and the right side of negative 3, and it approaches 0. Okay? And then similarly, we have the x plus 3 here, and as x approaches negative 3 from the left and the right, we notice that it also approaches 0. So they both have a limit of 0 separately. But the issue there is you end up getting 0 over 0. Okay, that doesn't really tell us anything there. All right, so Hopital saw a pattern. Okay, so take a look. What he did was, here's what he noticed. He noticed that when he was finding the derivative, the equation of a line right at -3. So pretty much where the limit as x was approaching -3, right? So he thought, well, you know what? Let me come up with a tangent line. You guys will see right here in green. Okay, that is the tangent line, right? The derivative of f of x at -3. Okay, so, I mean, you don't have to worry about how I wrote on the left over here. But here's what he noticed. He noticed that if we got arbitrarily close, okay, so right now, I can definitely tell which one is the parabola and which one is the line, okay, besides the color, okay? They definitely separate. But he said, Hopital said, if we got arbitrarily close, okay, besides the color, you can't really tell which one's which. They actually overlap, okay? So if we're close enough, the derivative behaves just like the function. All right? Where am I getting at? I will get there, you guys, all right? And then he looked at the other function and he thought, you know what? Let me find the derivative of that at -3. But if you guys remember, the derivative of that is just another line, okay? So the derivative of g of x at -3 is just a constant 1, all right? And it produces this same line here. So here's what he figured out. Right here, so I'm showing both f of x and g of x. Right here at -3, both f and g have a limit of 0 as x approaches -3. But 0 over 0 gives us something undefined. So Hopital thought, well, you know what? Instead of looking at the functions, if we're close enough, the derivatives behave the same way. So can't we just look at the derivatives? So take a look here. Right there in green is our derivative of our red function. And right there in red, which isn't really popping up because it's underneath, is the derivative of the other function there, okay? So if we zoom in close enough, you can't tell which one's which. So this is the same thing as taking the limit of each of the derivatives. Okay, I'll say that one more time. Make sure you guys understand that, okay? Because applying Hopital's rule is easy, but understanding why it works is the important part, you guys. If we get arbitrarily close enough, okay, the derivatives behave just like the original function, okay? So here's what he figured out. So he said, as long as we can show that the function is indeterminate, meaning that it can't be determined, the limit cannot be determined, which is slightly different than undefined, okay? So I kind of lied to you guys. It's only because you guys didn't know enough yet, all right? So here's what he stated. He said, if a limit is indeterminate, then the limit of f of x over g of x as x approaches a is equal to the limit of f prime of x over g prime of x as x approaches a. Okay, that is the formal definition. So let me break this down for you guys, okay? First, just like with any theorem or rule, there is a condition. So if we can show that the limit is indeterminate, so first, what the heck is indeterminate? All right, indeterminate form comes in many different shapes, but the two most common ones are 0 over 0. You could ask Siri that If you ask Siri what's 0 divided by 0, she'll tell you as well. Or infinity over infinity. There are other indeterminate forms, but you won't see that until you get into upper math, okay? So for now, we'll just stick with these two indeterminate forms. So first, if you can show that the limit is indeterminate, so remember now when you guys see 0 over 0, you cannot say undefined, okay? You have to say indeterminate, all right? It can't be determined. You could use L'Hopital's rule. So if you can show a limit is indeterminate, you could use L'Hopital's rule, which is basically this. You can basically take the limit of the derivatives, okay? So let me show you in the same example that we just did here. This is exactly how you guys would do it. We're going to take the limit of 2x squared plus 7x plus 3 all over x plus 3 as x approaches negative 3. I'm going to directly substitute like always. Nothing has changed. I find out that it comes out to 0 over 0. Now, this is the minor detail that you guys have to catch. When you say equals 0 over 0, you have to say which is indeterminate. Do not write equals indeterminate, okay? Because when you write the term equal, you're equating it to a value, all right? So this is a minor detail that you have to pick up. So first, we already met the conditions of L'Hopital's rule. So now, we could just take the derivative of each. This is not the quotient rule, okay? So the limit as x approaches negative 3, I'm going to go ahead and take the derivative of the numerator here. Go ahead, press pause, and play when you're ready. That's just going to be 4x plus 7. Okay? Down below, right, the derivative of x plus 3 is just 1. Okay? Notice how I can directly substitute now. I end up getting 4 times negative 3 plus the 7, which gives me negative 5, which is what I got right up here. Okay, so this is an alternative way. Now, some of you may argue that the first way was better where we manipulated, because you guys are used to manipulating, right? Okay. So what's the purpose of L'Hopital's rule if we could just manipulate it, right? So the thing is, not all functions are easily manipulated. For instance, I think one of you guys, let me go ahead and erase this here. I think one of you guys asked this question a while back in one of the homework assignments, and I couldn't really give you a straight answer. I think it was either Charles or Houston, I forget. The question was the limit of sine x over x as x approaches 0. Okay, now before L'Hopital's rule, how would you really solve this one here, right? We try to directly substitute. We find out that the sine of 0 is 0 over 0. At that moment, you guys would have said undefined. But then what, right? There was really no algebraic manipulation that we could take care of here. So you were kind of limited, and I encouraged you guys to look at the graph instead, right? In which you found out that the limit was 1. Now, you guys have this added to your artillery here, okay? So if we have the limit of sine x over x as x approaches 0, I could use L'Hopital's rule, but I first have to show that the condition is met, meaning I have to show that it comes out indeterminate. So if we plug in 0 here, the sine of 0, if you look at the unit circle, is 0. And when x is 0, we get that. Remember, we don't write equals indeterminate, you guys. So we say which is indeterminate. And AP readers are actually very picky with that. Indeterminate. So make sure that you guys follow it. So that gives you the green light to use L'Hopital's rule, which is basically you being able to take the limit of each derivative, not the quotient rule, okay? Not Drake's rule. Okay, so the derivative of sine x is cosine x. The derivative of x is 1. Well, check that out. Cosine of 0 is 1. Okay, so if at first you thought, you know what, I'm going to just leave L'Hopital's rule to the side, I don't need it, you actually do. Because on the AP exam, they specifically choose problems where you're pretty much forced to using L'Hopital's rule. So let that be your best friend, okay? L'Hopital's rule is actually, I think, a lot easier than manipulating. But then again, that's just preference, okay? Let me give you another example here, okay? So try this one out. Here's example 1. I want you to find the limit of x squared minus x all over x squared minus 1 by applying L'Hopital's rule, okay? Now, here I understand you can manipulate it algebraically, but I want you guys to apply L'Hopital's rule here. And then press play whenever you're ready, okay? All right, first, if I plug in 1 mentally, this comes out to 0 over 0, which is indeterminate. Okay, then I could apply L'Hopital's rule. Equals the limit as x approaches 1 of the derivative of each of them are going to be 2x minus 1 over 2x. And I notice that when I plug in 1 now, I get 1 over 2. Okay, some of you are probably favoring L'Hopital's rule, okay? Give it a chance, okay? Let's try another one here. Here's part B. The limit of the natural log of x, I should curve that L because there's always a student that says, Mr. Lee, what's 1n? The natural log of x over x minus 1 as x approaches 1. Okay, go ahead and try this one out here. And press play when you're ready. All right. Okay, if I plug it in, if I directly substitute, I get the natural log of 1 over 1 minus 1. 1 minus 1 is 0. Natural log, the only natural log value you need to know is the natural log of 1. And the natural log of 1 is 0, okay? Make sure that you guys add that to your tool belt. All right? What does that tell us? That tells us that this is definitely indeterminate. Okay, we can't figure out what that value is, what 0 over 0 is, right? So what do? We apply L'Hopital's rule. Okay, so the derivative of natural log of x, try to remember these, but if you forgot, refer back to that calculist of formulas. Pun intended. The natural log of x is just 1 over x. The derivative of x minus 1 is just 1. Okay, so if you plug it in here, if you plug in 1, you're just going to get 1 over 1 over 1, right, which is 1. So we did determine what that value is. Okay, so we went from indeterminate to determined. All right, let's try a couple more. Here's what you may see. Here's part C. We have the limit of e to the x over x squared as x approaches infinity. All right, so a little bit new here because you're approaching infinity here. Usually you're approaching a finite value. So graphically what's happening here, you guys, just so you know, is you're going all the way to the right. So when x is approaching infinity is, you want to see what happens to the graph when you go all the way to the right. All right, but we're going to do the same thing. We're going to plug in infinity, even though it's not a finite number. Okay, e to the infinity is just infinity, just some large number. Infinity squared, if you square infinity, you still get some type of infinity, right? Infinity over infinity is another form of an indeterminate. So we can state that this is indeterminate, okay? Which gives us the green light to use L'Hopital's rule. So that tells me that I can take the limit, let me erase that. Okay, I can take the limit as x approaches infinity of each of the derivatives, okay? The derivative of e to the x, take a look at your list or try to recall it, is e to the x, okay? The derivative of x squared is 2x, all right? Then we plug and chug here, we directly substitute. We get e to the infinity over 2 times infinity. We still get some type of infinity over some type of infinity, okay? 2 times infinity is not 2 infinity, okay? 2 times something that's infinite gives you something infinite. So we run into a situation here where it still is indeterminate. So you know what? You can run it again. And sometimes you got to run it a couple of times. So we're going to run it again. We're going to take the derivative one more time. The derivative of e to the x is just e to the x. And the derivative of 2x is just 2. All right? Now when I plug and chug here, I get e to the infinity over 2. Infinity is in the numerator, and 2 is just 2. Well, what's infinity divided by 2? That's just infinity. Notice how that is not indeterminate. Okay? What does infinity mean? The limit does not exist. Okay? So sometimes you don't get a perfect answer. Remember, certain limits don't exist. Certain limits do. All right? But keep in mind that if I gave you guys this problem back in Unit 1, there would be no algebraic way of solving this. Okay? You could probably graph it if you had the opportunity to do so, but remember, certain problems, they don't always give you access to a calculator, so just keep that in mind, okay? I think one of you guys mentioned that in your video, which is awesome. A lot of us thought that the graphical approach was good for their problem because you can see it, but remember, this is assuming that we have access to a graphing calculator. On the AP exam, there's a non-calculator portion and there's a calculator portion. So don't always rely on one approach. You got to be a little bit flexible depending on what is provided. All right. Okay, that's Hopital's rule, you guys. So again, you can only use it if you show that it's indeterminate. It's pretty cool. I think it's a nice alternative to manipulating. Okay. But remember that not all problems can be manipulated. So you have to rely on Hopital's rule. Okay. And please don't say Hospital's rule. Cool. We're going to revisit limits now, all right? Actually, let me go back to the very beginning and check this off. So we have Hopital's rule. Okay, limits. So remember that the derivative, the limit definition of a derivative, go ahead and write that down. Try not to look back. The derivative was the limit of f of x plus h minus f of x all over h as h approaches 0. Okay? We have this super long definition. You guys did it in like homework 1 or 2. And it took about 5 or 6 steps for you to clean it up algebraically, and then you got your answer. And then in the next few sections, you find out that there's a billion type of shortcuts. Right? So what's the point of this? Can we just drop this and let it go? Right? Not really. Okay? So here's what the AP exam or AP readers want you to understand about this definition. Okay? For instance, let's say I asked you, what is the limit of sine of x plus h minus sine x all over h as h approaches 0? Okay, go ahead and figure that one out. Pause there and figure out this limit. All right, and press play when you're ready. Okay, so here, actually, if you plug in 0 for h, you're going to get sine x minus sine x, which is 0, all over 0, which is indeterminate. By all means, you can definitely use Hopital's rule here, right? Or you understand that this is a limit definition of a derivative. You guys have to understand that this is translated as what is the derivative of sine x. And that's what they want you guys to understand here, okay? This is the perfect setup for the limit definition of a derivative. So what you can do here is this. Now, some telltale signs. I noticed that when h is approaching 0 and I have some type of function x plus h, some type of x all over h, that is basically your limit definition of a derivative. So right away, I know they're just asking me, well, what's the derivative of sine x? The derivative of sine x is cosine x. Okay. If you use Hopital's rule, you will probably get your answer, but it will take you probably an extra minute or 2 or 3. Okay, and especially on the AP exam, you don't have any second to waste. So you want to be as efficient as possible here, okay? So if I ask you guys, what's the limit, okay? What's the limit of e to the x plus h minus e to the x all over h as h approaches 0? Go ahead and try that on your own, but it shouldn't take you more than 5 seconds. Okay, this is just code for what's the derivative of e to the x. Derivative of e to the x is just e to the x. Okay, so what I'm getting at here is you got to be able to recognize when you have a limit definition of a derivative. Okay, again, they have h approaching 0 all over h. You got some x plus h and some x. Notice how they have the same components, okay? So here's part C. What's the limit of the natural log of x plus h minus the natural log of x all over h as h approaches 0? Figure that out in under 5 seconds. Okay, that just comes out to 1 over x. Now, if you're not seeing it, you got to let me know. Don't run Hopital's rule here, unless you accidentally forget that it is a limit definition, okay? So we're pretty much trying to shed some time so that you can use that somewhere else, all right? Do I have any more? Let me take a look. Oh, okay, here's another one. Not too transparent, but I want you guys to try this one out. The limit as h approaches 0, okay, of 1 over the quantity x plus h squared minus 1 over x squared all over h. Go ahead and try that out. Press pause here, and then play when you're ready. Okay, so I understand that this is a limit definition of a derivative because I have h approaching 0, I have an x plus h, I have an x, I have an all over h. It looks just like the limit definition. So basically they're asking me what's the derivative of 1 over x squared. So on the side, 1 over x squared I know is the same thing as x to the negative 2. And the derivative of that is just going to be negative 2x to the negative third, or negative 2 over x cubed. Okay, I prefer the one with non-negative exponents, okay? Okay, here's one more before we move on to the next one. The limit as h approaches 0 of arc tan of x plus h minus arc tan of x all over h. Go ahead and try that one. Okay. Now you might have had to look at your calculus, but pretty much what's the derivative of arctangent? It's just 1 over 1 plus x squared. Okay. It's one of those things that you just gotta know. All right. So there you go. Revisiting limits. Just understand when you have a limit definition of a derivative. A telltale sign is that h is approaching 0, right? But also when you have some type of x plus h term. Okay, so just keep that in mind. It could save you a lot of time there, okay? All right, so we revisited limits. Cool. Okay, on to higher order derivatives. Higher order derivatives is basically when you take derivatives multiple times, okay? So suppose you had a function, okay? The derivative would be written as f prime of x, okay? The second derivative would be f double prime of x. Notice how I'm saying it, okay? The third derivative would be f triple prime of x, okay? And then it was decided that when you get to a higher order derivative, okay, you would write it as f, but you got to use parentheses here with the 4 of x, okay? The way you read that is the fourth derivative, okay? Okay, so that parentheses right there, remember the parentheses indicate that that's a derivative, okay? So just keep that in mind. Now, I always mix these two up. I believe this is Lagrange notation, okay? Lagrange is when you use the prime notation. Now, Leibniz notation is a little bit different, and you guys got to pay close attention to the details here, okay? So, another way of writing f of x is y. This is the other notation. You guys find it very beneficial, especially when you're using implicit differentiation, okay? So the derivative of y is the derivative of y with respect to x, dy over dx. Now, when you get to the second, third, and fourth one, pay close attention to how I write this because I didn't make a mistake, okay? The second derivative would be the second derivative of y with respect to x twice. Notice the placement of the 2's. All right? The third derivative would be the third derivative of y with respect to x 3 times. Okay? Fourth derivative of y with respect to x 4 times. So Leibniz notation, you got to be very careful where you put those exponents, if you will. Okay? So just get used to the notation. So for instance, here's an example. If I told you that y is sine x, they may ask you, well, what's d4y over dx4? Okay? You guys got to know what that really means. Okay? That just means the fourth derivative. Okay, so here we go. Go ahead and help me out here. dy over dx is what? What's the derivative of sine? Cosine. Okay. Well, what's the second derivative? Okay, what's the derivative of cosine? Negative sine. You guys got to watch out for that, okay? Well, what's the third derivative? Well, the derivative of sine is cosine, so that's just negative cosine. That's just the constant multiple rule, okay? Well, if that's the third derivative, what's the fourth derivative? Okay, well, if I just look at cosine, the derivative of cosine is negative sine, so that's negative sine x, which is really just sine x. All right, and that's it. So higher order derivatives, know the notation and know how to actually find derivatives, okay? Please do text me throughout this, okay? Especially if you're a little bit lost, and that's okay. Just be very transparent with me. It's a little bit tough with distance learning because normally in the classroom, I'll probe you guys with questions. I'll ask you a lot of questions, but it's kind of tough to do that, you know, through distance learning. So I encourage you guys to ask questions for clarity, okay? Even if you think you know it, just for that little bit of confidence, ask, all right? Okay, so we have higher order derivatives taken care of. Here's the last piece. Not bad at all. Parallel normal lines. So first, let me show you what parallel normal lines are. You guys have seen the word parallel. You might not have seen normal, all right? But let's say you had a curvy function. I like to pick a parabola because that's the easiest one, okay? And you guys should draw this out too. Now, suppose we have this. what do we call that line, right? Okay, a line that intersects a curve once, we call that a tangent line. Okay, so oftentimes there will be questions that will ask you, find the equation of a tangent line that's parallel to another line. So basically, they're going to ask you, well, find me that green dotted line and make sure that it's parallel to this random other line over here. Okay, definitely parallel. Okay, so you got to revisit what you understand about parallel lines. Way back in Algebra 1 or Integrated 1 or Integrated 2, it pops up in pretty much every class. But parallel lines are lines that don't touch, okay, or don't intersect. That's a more formal term. Parallel lines have the same slope. So make sure that you guys are writing this down. Same slope. So I'm going to give you an example here. I'll give you a chance to write down the problem. Let's say we want to find the equation of the tangent line to the curve of y equals x squared plus 10. That is parallel to the line y equals 8x plus 7. Okay, press pause, play when you're ready. Okay, so here's what we do. You guys have seen this phrase before, equation of the tangent line. I've been bugging you guys about it in a lot of videos. What do you need to make an equation of a tangent line? Okay, we need a slope and a point, right? Okay, so notice here, they don't really give us much, all right? Kind of. So they tell us that we need to make a tangent line, okay, that's parallel to this line right here. Well, conveniently, if you remember, this line here is written in slope-intercept form. So can't you tell me what the slope is there? Pause and press play when you're ready. So I know the slope of this line y equals 8x plus 7 has a slope of 8. So I know that my new line has to have a slope of 8. Okay, so all I'm missing is a point. Okay, now this 8 is going to represent the slope of a tangent line. Anytime you're dealing with a tangent line, you're dealing with a derivative. So here we go. We have to find the derivative of the curve because you're trying to find the slope of the tangent line, okay? So y prime here, go ahead and figure that out, is 2x, okay? But the thing is, don't I already know what my slope is? I do. My slope has to come out to 8. So remember, y prime means slope or derivative, right? I know that I want my derivative to purposely come out to 8. So now your job, you guys, is what you're doing is you're now trying to find out where that point is. Okay? So you know the slope. So this gives you an opportunity to solve for the x coordinate. Okay? If you solve for x here, you find out that x comes out to 4. Okay? So right away, I know that this is 4 comma something. Okay, so how do I figure out what I'm missing? The y value. Okay, remember this point. Now here's where some people get mixed up. They see a lot of equations. They're not really sure where to plug in this value. If you take a look at this picture, right? That point is it on the parallel line or is it on the blue curve, right? It's on the blue curve, so it only makes sense to plug it back into that curved function, which is the parabola, or the x squared plus 10. So here we're going to have y equals x squared plus 10, but now we're going to plug in the x coordinate of 4. All right, so this ends up giving us 26, which is our y value, okay? We know it's going to be parallel because they have the same slope, all right? So all that's left to do is to make that equation of a line. It's going to be y minus the y coordinate, 26, equals the slope, 8, times x minus the x-coordinate. No need to put in slope-intercept form. Okay, you could just leave it right there. Okay. All right. Now, we introduce this term here, normal. Go ahead and write down this problem, and then I'll talk about normal. Okay. Now, a normal line is very specific. It is I'll draw it in pink here. It is a perpendicular line, okay, a line that is perpendicular specifically to the tangent line. So it's perpendicular, so we call that the normal line. So normal and perpendicular are not exactly the same, they're similar. Normal is specifically where the line is perpendicular to the tangent line. All right? So just a minor detail, that's all. So we can say that a normal line is perpendicular to the tangent. Okay, so we got to revisit a little bit here, okay? If you recall, lines that are perpendicular create a right angle, but there is a relationship with their slopes. Kind of like parallel lines, we know that they have the same slope. Perpendicular lines, Google it if you have to, okay, have opposite reciprocal slopes. Or sometimes they call it negative reciprocal, but that's so misleading, okay? So for instance, if the slope of my tangent line is positive, let's see, let me pick a number here, positive 2/3, the normal slope, notice how I'm writing that, okay? Or the perpendicular slope to that tangent line, what you do is you take the opposite, so you flip your signs, so that positive becomes a negative. And then reciprocal means you flip the fraction, okay? So that becomes -3/2, all right? Let's do a couple here. I want to make sure that we're good with that concept before we actually do number 2 here. So if I told you that the slope of the tangent line is -4, okay? Pause and press play here. Go ahead and figure out what that normal slope would be. Okay, that normal slope would be opposite, so it's going to be positive. And the reciprocal of 4 is 1/4 because it's 4/1. Okay, hopefully you got that. Let's do one more. If the slope of your tangent line is +6, okay, think about what that normal slope is. Press play when you're ready. Okay, it'll be opposite, so negative, and it'll be the reciprocal, 1/6. Not that bad, okay? So we're going to use that concept. Here we go. We have an equation of the line normal to the graph of, what equation did I use here? Oh, okay, to the graph of y equals x cubed plus 3x squared plus 7x minus the 1, okay? I don't know why that part got erased, but go ahead and write that down. Sorry if you have to erase or squeeze it in. Okay, so we go back to the same idea here. How do you make an equation of a line, you guys? What do we need? Okay, we need a point and a slope, or a slope and a point. I'm just going to label that there. The moment we figure out what these two parts are, we can make a line and we're all done. Okay, what are we already given? Okay, so an equation of the line normal to the graph of this curve at the point where x equals -1 is. So based on this here, we know the x-coordinate is -1. Okay, so we're missing the y-coordinate and we're missing the slope. Okay, so we have this cubic function. I don't necessarily know what it looks like, and we know the x-coordinate is at -1. How do we figure out the y-coordinate? Well, all we do is, since this point is on the curve, we're going to plug it into the curve, right? So here we go. Y equals -1 cubed plus 3 times -1 squared plus 7 times -1 minus 1. Okay, a little bit of evaluating. Here we go. We get -1 plus the 3 minus the 7 minus the 1. -1 plus 3 is +2, minus the 7 is -5, minus 1 is -6. Okay, so what does that represent? That's our y coordinate. Okay, so we just found out that the y coordinate is -6. So we're halfway there. All we're missing is a slope. Well, how do you find the slope, right? How do you find the slope of a tangent line? Okay, you need to go to the derivative. So here you go. Y prime equals, press play when you're ready, okay? But try that one out. Y prime equals 3x squared plus the 6x plus the 7. Okay? Now, I need a slope, so I need a value. This right here is just my general slope. Right? So what do? Okay? I have to evaluate this where? Where exactly do I want to find my slope? I want to find my slope exactly at where my point is, right there. Okay? So I am going to evaluate y prime at -1 comma -6. Okay, that'll give me 3 times -1 squared plus 6 times -1 plus the 7. Oh gosh, what does that come out to? That's 3 minus the 6 plus the 7. That should give me a +4. Okay. Here we go. What does that represent, that +4? Okay. What did we just find? Right? We found the derivative. What does the derivative mean? That is the slope of the tangent. But the issue here is we're not interested in the slope of the tangent line. We're interested in the equation of a line that's normal. Okay? So remember how normal lines are in relation to the tangent line. Okay, they're perpendicular. So if we know the slope of the tangent line, we should know the slope of the normal line. Okay, press play when you're ready. That's just going to be negative, opposite, and then the reciprocal. And that's exactly what you're going to use right there. So now we know that the slope is -1/4. So my equation, which I'll write in dark blue here, is going to be y minus -6. So that's going to be y plus 6 equals the slope times the quantity x minus -1, which is x plus 1. There you have it. Okay? These are some things that you'll definitely run into. All right? Parallel lines have the same slope. Normal lines are opposite reciprocals or perpendicular to the tangent line. Okay? But if you notice, nothing has changed. We still need to find a point and a slope. Whenever they ask you for an equation of a line, if there's one thing I can teach you in calculus, equation of a line, you need a point and a slope. All right? Point and a slope. This question you will see pretty much in every unit. So don't forget that, okay? So that's it, you guys. We were able to explore Hopital's rule, which is another way of finding limits. We revisited limits and understood that whenever you see a limit definition of a derivative, you could take your shortcut. Higher order derivatives, you're just taking derivatives in higher order. You're learning how to write it in Lagrange and Leibniz notation. Don't worry about spelling those out, but just understand how they represent the problem there, okay? And lastly, understanding what parallel lines do and how they behave, as well as normal lines, all right?